Okay, so let's start. So in this class, we'll essentially wrap up the proof of the fundamental theorem of pack learning for binary classification. Recall that in the last couple of classes, we were trying to prove a bound on the generalization error for every hypothesis in the class in terms of the VC dimension. That's the end goal. And we saw a bound on the generalization error in terms of two other parameters of the hypothesis class. Firstly, we saw that the generalization error can be upper bounded by the empirical risk plus some function that depends on epsilon, delta n, and the Rademacher complexity of the class, right? That's a fundamental bound, and this bound is true for any supervised learning problem with a bounded loss function. So it's pretty powerful, and you can use this, for example, for even regression. And in fact, people do make use of similar types of bounds. All right. But since we're interested specifically in binary classification, we can further upper bound the Rademacher complexity in terms of the growth function. We saw that the Rademacher complexity can be upper bounded by square root of 2 times log of the growth function divided by n. Yeah. Yes.
Final example.
Correct.
That is it would not 70, right? What time would it be?
In class.
In class.
Yes. Okay. So last class we are going to have the example.
Will be 6 to 9 on top of the game.
Sure. So it'll be in class. We start around 4:10 or something.
It would be a 1 hour exam, right? Like last time for
1 hour, 10 minutes.
Okay, like will it be starting late?
I'm sorry?
Will it be starting late?
We will try to wrap up by 5:30.
By 5:30?
Yes.
And yeah, by 4 we have to come.
Yeah, 4, 5. 5 minutes is okay. Okay. So we're looking at bound on the Rademacher complexity in terms of the growth function and this holds true only for binary classification. And therefore that gives us a bound on the generalization error in terms of the growth function. Right? So up to the last class, this is what we had. Now the problem is that neither the growth function nor the Rademacher complexity can be very easily computed for arbitrary hypothesis classes. Right? So in this class, we'll prove a bound on the growth function in terms of the VC dimension. So the main bound is this result by Sauer and Shelah. Which says that the growth function for any hypothesis class can be upper bounded by summation I equal to 0 to the VC dimension of n choose I. Okay, so once we have this, we automatically get a bound on the generalization error for any algorithm. Any questions? Question? All right, so let's see how to prove this. This requires some neat combinatorial tricks. So in fact, we'll prove a slightly stronger result. We'll show that for any, so let's quickly recall the definition of the growth function. The growth function of a hypothesis class is the size of the largest restriction of H onto subsets of size n. Max overall xn subset of the domain such that xn has size n of the restriction of the hypothesis class onto xn. So in fact, we'll show something a little stronger. It is that it doesn't matter what subset you choose, not just necessarily the maximal subset, but for all xn, the size of the restriction can be upper bounded by the number of subsets of xn that are shattered by H. Right? Just recall that a set is shattered by H if the restriction of H to that particular set is the set of all possible functions. Right? Or in other words, the size of the restriction is 2 to the power the size of the set. Right? So this is the number of subsets of xn such which are shattered by H. Now, if suppose that xn is itself shattered by H, right? Then what is the number of subsets of xn which are shattered by H? 2 to the power n, and why? All subsets, right? And what does that correspond to? So this, what does this particular quantity give? Yeah, correct. For n less than d, it will always be 2 to the power n. So now you see that this kind of holds. Now let's so for n less than d, it's anyway true, right? What about n greater than d? What does the right hand side evaluate to? Right? Or in other words, suppose that n is greater than d. So I want to say that the number of subsets of xn that are shattered by H is upper bounded by this particular quantity. All right? And why is that true? So if a subset of xn is shattered by H, right, then what is the size of the largest subset that is shattered by H? D, right? We see dimension, right? So any subset of size larger than D cannot be shattered by H. Any subset of xn having more than d elements is not shattered by H. Right? So the number of subsets of xn which are shattered by H is at most the total number of subsets of a set of d elements. Right? It can't be any more than that. So one thing to note is that, so just remember that the VC dimension is the size of the largest subset of X which is shattered by H. Doesn't mean that all subsets of size D are shattered by H. Right? So So in particular, for this for a certain xn, the number of subsets of xn that are shattered by H could be much smaller than this particular quantity. You have a question? Yes. No, there exists one subset of size D which is shattered by H.
For greater than D,
For greater than D, every subset, no subset of size greater than D can be shattered by H. Alright. So this can simply be upper bounded by the number of subsets of a set containing D elements. Subsets of Xn having at most D elements. So in this bound, this bound is true because in the worst case, every subset of size less than or equal to D could be shattered by H. Right? So if I'm able to show this particular statement, then I'm done. Right? You agree with me? Okay. So now all I need to show is that the growth function, or more generally, the size of the restriction on any subset of n elements is upper bounded by the number of subsets of Xn that are shattered by H. All right. So to do this, I'll define a bunch of different sets. So the proof is essentially via induction, right? What happens if, of course, we've seen that if n is less than or equal to D, then this bound kind of holds, right? But in any way, let's start with n equal to 1. All right. What is the right hand side for n equal to 1? Or what is this equal to when n is equal to 1? 2, right? And what is the size of the restriction? Onto any one element. It can either be 1 or it can be 2. Okay. Which one? You mean to say this inequality?
Yeah.
Okay, great. So I want to count the number of subsets of Xn which are shattered by H. So every subset of size greater than D cannot be shattered by H, right? A subset of size less than or equal to D may be shattered by H, may not be shattered by H, correct? So an upper bound is an upper bound on the set of subsets which are shattered by H is simply the number of subsets of Xn of having size at most D. Right? In the worst case, all of them could be shattered by H.
Alternative of H is equal to sigma equal to 1 to D.
No. I'm saying that this quantity is upper bounded by this for the moment. The number of subsets of Xn which are shattered by H is less than or equal to this. That's all I'm claiming at this point.
Won't that reflect that alternative H?
Correct. But I still have to prove this particular statement.
Okay, we didn't rigorously do it.
No, we have not proved it at all yet.
We talk about the 2 power n and
that's only if n is less than D. That's only true if n is less than D.
For n greater than D,
I have to prove it. I have not proved this particular. So
less than or equal to more.
Yeah, we will show that this quantity is less than or equal to this.
Less than is for sure, but less than or equal to is not sure. That's it. Right?
So if less than, I'm more than happy,
Yeah.
but it can be equal to this.
Okay.
But why do you say that this is less than this for sure?
Like if for n greater than D, that alternative Hxn will be less than 2 per D, right?
But this is not 2 to the power D, right?
But 2 to the power D will be less than 2 to the power n. because n is greater than d.
2 to the power d
It
is
will be less than 2 power n.
okay, but this is not 2 to the power n.
That is
Correct. In general, no, right?
okay. That is shattered by h. Okay.
That is shattered by
Yeah.
h, right? It's not the number of subsets of
Yeah.
xn. Yeah.
If the basic dimension is d,
Correct.
are we also guaranteed that for all n less than d, like strictly less than d,
Correct.
it is completely shattered by h, or is it possible that not all are shattered?
Not all are shattered by h.
So even if there exists like one for each of the dimensions,
Correct.
we still keep like increasing the like checking the next.
So the growth function looks at the largest restriction, right? Even if there is one subset which is shattered by h, then the growth function for that particular n is 2 to the power n, right? So the growth function is essentially, it grows as 2 to the power n up to n equal to d, and then after that you don't know what happens. It's something which is less than 2 to the power n, but we're not entirely sure, right? But this gives a concrete bound, right? So in fact, what this essentially says, we'll see that a little bit later, is that for n much larger than d, this grows just polynomially in n. So in some sense, there is kind of a phase transition. It grows exponentially in n, and beyond the VC dimension, it grows only polynomially in n. Right? Okay. So right now, what I want to prove is that the size of the restriction to any subset xn is at most the number of subsets of xn which are shattered by h. Right? Let's just take n equal to 1. N equal to 1. Okay. What is the number of subsets of xn that are shattered by h? The null set is shattered by. We'll assume. Right. So how many subsets are there for a singleton? 2. Right. One is the null set. The other is the set itself. Okay. So if you have a function that is non-trivial and it takes, so basically if h takes on 2 different values on xn on that singleton, then the right hand side is equal to 2, right? Because it's a singleton, it gets shattered by h, and the left hand side is the size of the restriction. If it takes on 2 different values, then that's equal to 2. Correct? Are you convinced? Okay. So now let's assume that this statement is true for up to n minus 1. If I'm able to show with just this that it's also true for n, then I'm done. By induction, I can claim that the statement is true for all possible. When I say that the lemma is true for all n prime, I'm saying that it is true for all subsets of size at most n minus 1. the restriction onto xn minus 1 is less than or equal to number of subsets of n minus 1 scattered by h. Okay, great. Now let's consider an arbitrary xn consisting of n elements. From this, I'll construct two subsets. I'll call them y or, which is the set of all y1, y2 up to yn minus 1 such that minus 1, this is in the restriction, right? So what is hxn? Hxn is simply, it's just a collection of 0, 1 vectors, right, of length n. Let me rewrite this a little.
Y4.
I'm sorry? Yeah, y subscript or. Alright, so it is that collection of 0, 1 vectors of length n minus 1 such that when appended with either 0 or 1 makes it an element of the restriction of h onto xn. And I'll also define this set y and in a similar fashion. So it's a set of all 0, 1 vectors of length n minus 1 such that when appended with both 0 and 1, they belong to the restriction hxn. Okay, it's just a definition. All right, we'll see why this is useful in a moment. Now I'll define another set. Let me call this h prime. So it's another hypothesis class, and it will be a subset of the original hypothesis class. And this is essentially the set of all hypotheses such that there is some alternate hypothesis. So for every h in h prime, there is some other hypothesis in the original hypothesis class such that if you look at h of x1, h of x2 up to h of xn, this basically agrees with h prime in all except the last element. So up to the last element, everything is the same, but the last element is just the opposite of what h predicts. The first few elements are exactly the same, but the last element is the opposite. Okay, so x1 so it basically comes from this subset, right? We fixed n elements. Right? You want, just think of them as n training samples if you like. It's not really the training sample, but you have n samples, and on the first n minus 1 samples, the two hypotheses are exactly the same. On the nth sample, they're exactly the opposite. Sorry. So if h predicts xn to be correspond to 1, then h prime predicts it to be 0, and if h predicts it to be 0, then h prime predicts this to be equal to 1. Oh, sorry, it's h dash of x. Yeah. Okay. So now suppose that h prime shatters some we call this x double prime, which is a subset of the first n elements. Okay, so I take an arbitrary subset of the first n minus 1 elements of xn, and let us say that for this particular subset, h prime shatters this. All right, what can I say about x double prime union xn? Does h prime also shatter x double prime union xn? It does. Why?
It's
Correct.
have
Correct. Exactly.
and both belong.
Exactly. So in this condition, if some particular h belongs to h prime, then this little h prime should also belong to h prime because this relation is symmetric, right? So h prime also shatters x double prime union xn. Okay, so now what can you say about the set y and? Right? Can I claim that y and, so recall that this is the set of all possible functions on n minus, or in other words, you can think of this as a set of restrictions onto n minus 1 elements such that when appended with 0 and 1, they still belong to hxn. So my claim is that this is equal to the restriction of h prime onto this set xn minus 1, which is the first n minus 1 elements. Yeah. So let's look at the definition of y and. Just compare this set with this set. So if a binary vector is in y and, what should happen? There should be some h and some h prime such that h of x1, h of x2, and so on is equal to this particular vector. And there should be at least some other h prime such that h of x1 through h of xn is equal to this particular vector, which is exactly the statement over here. Right? So in fact, these two sets are the same, y and this h prime. So the number of elements in this set y and is equal to the number of elements of in the restriction of h prime onto xn minus 1. But how many elements does this contain? Does xn minus 1 contain? Less than n, right? It contains n minus 1 elements. Now I can use the induction step. So this is at most the number of subsets of xn minus 1 that are shattered by h prime. Not h. I'm sorry?
What is it?
It's the restriction of H prime. This is H prime, right? So this is a subset of the hypothesis class. Xn minus 1 is basically this set. X1 through Xn minus 1. Only the first n minus 1 elements of Xn. It's the same, right? So it's again a set. It consists of vectors of length n minus 1. Which one? These two sets are equal. Yeah. Correct.
Constraint H.
So I'm assuming that no matter what the hypothesis class is, it's still true. Right? So this particular statement that I'm making in the induction step is that this statement is true for all H. So you take any hypothesis class H and any subset of X of size n minus 1, the restriction of H onto Xn minus 1 is at most the number of subsets of Xn minus 1 that are shattered by H. Okay? Because for n equal to 1, this is true no matter what H and what Xn is. Correct? So let's suppose that this is true for all H, for all sets of size n minus 1. Okay? So this is at most the number of subsets of Xn minus 1 that are shattered by H prime. Right? So if recall that Xn minus 1, so if some set of Xn minus 1 is shattered by H prime, then H prime also shatters that set union Xn. Correct? So this is less than or equal to the number of subsets of Xn that contain Xn and are shattered by H prime. Because if any subset of Xn minus 1 is shattered by H prime, then if I add this last element to this Xn minus 1, then it is also shattered by H prime. Correct? Okay. Now if a set is shattered by H prime, recall that H prime is only a subset of H. Right? It's a subset of hypothesis class. It's a subset of the original hypothesis class. So this is less than or equal to the number of subsets of Xn that contain that last element little xn and are shattered by H. Question? So H prime is some subset of the original hypothesis class.
Then shatter some.
Correct.
Then basically it's collection of all possible mappings.
Correct.
Like that, the subset of H.
Correct. So H contains more functions than H prime. Right? You agree with that? Right? So now if I'm looking at the restriction onto something, if H prime shatters a subset,
Then H prime and
which the restriction of H prime and the restriction of H onto that set are equal.
that is it, but H prime already is the set of all possible.
H prime is not the set of all functions, right?
Okay,
So
is one.
no, you have to be a little careful. So you're looking at, so you consider a some subset, right? Let's call it X double prime, right? So if H prime, so H prime is a subset of H, right? If this shatters some set, some X double prime, okay, then it means that the restriction of H prime onto X double prime, this is the set of all possible functions, right? So this is, in other words, H of x1 up to H, or H prime of x1 up to H prime of some xl, where x1 through xl is this, right? Right? So if this H prime belongs to H prime, then H prime also belongs to H, correct? So every vector that can be generated using a H prime can also be generated by a H. So if H prime shatters this X double prime, then H should also shatter X double prime. And that's the property that I'm using in this last inequality. There could be some subsets which are shattered by H but not shattered by H prime.
That way they're less than or equal to.
That's why it's a less than or equal to.
Here it is specifically X and K.
Correct. All right. So this is one step, right? So this is y and this is less than or equal to this particular quantity. Okay. Now let us look at y or, right? So it's the set of all vectors that can be generated by appending either a 0 or a 1 to, and it still lies in Hx. Right? So if some element of y or can be generated, let me copy this here. So this I claim is equal to the restriction of H onto xn minus 1. True, right? So if this has to happen, then it must mean effectively this statement, this or statement, is the same as saying that there exists some H such that y1 through yn minus 1 is equal to H of x1 through H of xn minus 1. Right? Because for xn you don't care what the value is. Okay, But now this is a restriction again on n minus 1 elements. So I can again use the induction step. Of subsets of x n minus 1 that are shattered by h. This is again just by induction. I can say that it's equal to the number of subsets of xn minus the last element, because that's what xn minus 1 is, right? That are shattered by h. Okay, so now let's look at h xn, the restriction of h onto xn minus 1. What can you say about that compared to y or and y and? If I take the union of y or and y and, what do I get? Right? You just get hxn, right? Because if I take the union, what does it say? y1 through yn minus 1. All right. So again, these look at y1 up to yn minus 1, right? Or in other words, n minus 1 vectors. Right? For the nth vector, for the nth element, either one of those two could lie in hxn, or both of them could lie in hxn. So hxn is simply y or union y and. Which one? No, hxn, right? Correct. But then this also tells you something about yn. Correct?
I mean, we need to append the y
Which one?
for it to be equal to that.
Correct. You'll also need to append
Yes,
yn.
yes,
Correct. So, okay. So I should be a little more careful. It's not exactly the union, but what I can definitely claim is that, so because after all, these are vectors of length n minus 1. I can say that the size of hxn is less than or equal to the size of the union. Why how?
Yeah, I get that y1 till yn minus 1 0.
y1 to yn minus 1 0, okay,
and y1 till yn minus 1
okay,
in this set.
which one? Okay, so suppose y1 through yn minus 1, let me make it more precise. I claim that this is this plus y n, okay. So now if y1 through yn minus 1 comma 0 is present and y1 through yn minus 1 comma 1 are present, then this is 1. So that is, so y1 through yn minus 1 is certainly in this particular set, and that is also present in this, correct? But if y1 through yn minus 1 0, only one of y1 through yn minus 1 0 and y1 through yn minus 1 1 are present, then this counts a 1 but this counts a 0.
So it's not exactly half.
It's not exactly half.
That's why
I'm sorry?
why am
Y
Y and this.
y and is a subset of y or, correct. I agree, yeah, correct.
This is y1.
Yeah, so really the statement I should be making is that the size of hxn is, in fact, it is equal to the size of y or plus the size of y and, right? Because if,
you just combine
exactly, if y1 through yn is in
Double count.
hxn, yeah, which one
Double
is it?
counting some element.
The point is that you will not double count. The reason is, suppose that y1 through, so suppose that this belongs to hxn, okay, then what can happen? Y1 through yn minus 1 0, y1 through yn minus 1 1. At least one of these two must belong to hxn. You agree with that, right? Suppose that both of these belong to hxn, right? Then y1 through yn minus 1 belongs to y or, and y1 through yn minus 1 belongs to y and, right? So you're counting exactly two elements, which is this and this, correct? It's equality there. So if, suppose that only one of these two belongs to hxn, then y1 through yn minus 1 belongs to y or, but y1 through yn minus 1 will not belong to y and. So you're counting it exactly once, right? So this is in fact an equality. Yeah. Which part?
Where you written hxn minus 1 is equal to y or.
Hxn minus 1 is equal to y or, yes.
In case, so let us say that the cardinality of hxn minus 1 is some unknown. In y or, the element that is added could either be a 0 or a 1.
Correct.
So that means there are m elements that have the same, that have 0 at the end, and m elements that have 1 at the end.
Not so we're only looking at this particular statement, right? So what is hxn minus 1? This is the set of all y1 through yn minus 1, correct? Which can be written as h of x1 through h of xn minus 1 for some h, correct? Okay, so suppose y1 through yn minus 1 belongs to this particular set, all right? So which means that there is some h, correct, such that h of x1 through h of xn minus 1 is equal to y1 through yn minus 1, correct? Now let's look at h of x1 through h of xn minus 1 comma h of xn, right? Now that belongs to, so h of xn could either be a 0 or a 1, right? So for this particular y1 through yn minus 1, there is some h that gives me this. Let's assume that I take some specific configuration 0 0 1 0 0. All right, so there is some h such that h of x1 is 0, h of x2 is 0, h of x3 is 1, and so on. So for this particular h, let's look at h of x1 and I'll append it with h of xn. Right? Now this could be 0, this could be 1, doesn't matter. But this vector lies in, so this can be generated by some particular h, correct? But which means that now this vector lies in hxn. Do you agree? Okay. But what does this statement say? So if y1 through yn minus 1 is in hxn minus 1, then y1 through yn minus 1 appended with that particular h of xn will lie in hxn, right? Which must mean that this also should lie in this set yr, because h of xn is either 0 or 1, correct? And the other way around, if some vector lies in yr, then y1 through yn minus 1 is also going to lie in hxn minus 1, which is more easier to see. Any other questions? Okay, great. So now we have hxn is equal to the size of yr and plus the size of yn. But we already have upper bounds on both of these sets. So what is yr? Subsets of xn minus the last element that are shattered by h plus what is an upper bound on y and the number of subsets that don't contain that contain xn that contain xn and shattered by h. Which is what? It's the total number of subsets of xn which are shattered by h. That just completes the proof of what we wanted to. Okay. So the growth function is upper bounded by summation I equal to 0 to d in choose I. n is upper bounded by summation I equal to 0 to n, summation I equal to d, n choose I. Now let's assume that n is greater than d, right? Right? Assume that n is, let's say, much larger than d. Then I can bound n choose I using n choose d if n is large enough. Okay, just to give you some intuition. Then this would be summation I equal to 0 to d of n choose d. But this is a simple upper bound for n choose d. This is upper bounded by summation I equal to 0 to d n e by d whole raised to the d. A much simpler bound on the binomial. Just look at n into n minus 1, so on. You expand it out, and then you'll see that you can simplify that as n e by d whole raised to d. But yeah, Stirling's approximation is something else you can use. Okay, so this is, sorry, less than NCD. So so let's look at n choose I. So if n is at least or if so suppose that n is at least 2 times d, right? Then okay, what kind of a function is n choose I? How does it grow with I? It increases up to roughly n by 2 and then keeps decreasing, right? So that's all that I've used. If n is, let's say, greater than 2d, then this statement is whole, right? And this is just d times n e by d whole raised to the d. So in the regime where d is some constant and n is like really large, this quantity just grows polynomially in n. Right? But you can prove something even stronger. And I leave this as an exercise. For all n which is larger than d, summation I equal to 0 to d n choose I is upper bounded by just ne by d whole raised to the d. You can just look up the textbook for the proof. Okay, so this book or one of the other textbooks, I think it's in. I'm sorry, just 1 second. Yeah, your question? You can't ignore it, but now I get an explicit bound in terms of d over here. Right? It's a simpler expression in terms of d. Yeah, so basically this is a very loose upper bound. This is a tighter upper bound on this, on the sum of these binomial coefficients. Okay, so now if I combine this lemma along with our previous bound on the growth function, what do I get? So what we've shown is that for any hypothesis class with VC dimension equal to D, the probability that the generalization error is less than or equal to, greater than or equal to the empirical risk for H plus square root of 2 times D log En by D whole divided by N plus square root of log 1 by delta divided by 2n. This is less than or equal to delta. Right, and this, I should be a little more careful here. The probability that this happens for at least one H in H, this is less than or equal to delta. So in other words, with probability at least 1 minus delta, the generalization error differs from the empirical risk by a very, very small amount. Which means that we have uniform convergence, right? Because D is fixed, it's a finite quantity. And if n is sufficiently large, how does this function grow? It's roughly log n, square root of log n by n. N grows faster than log n. So square root of log n by n goes to 0 as n tends to infinity. And this quantity is just some constant divided by 2n. So this whole epsilon tends to 0 as n tends to infinity. Right? And this statement is so as n becomes large, as n tends to infinity, the empirical risk is close to the generalization error for all the hypotheses in the class. So we have uniform convergence. So if the VC dimension is finite, then you have uniform convergence, which was what we originally set out to prove. So we wanted to show that if the hypothesis class has finite VC dimension, then it has the uniform convergence property. And therefore, ERM is an agnostic packed learner, and therefore H is agnostic packed learner. Question? Yeah, ERM is agnostic packed. I mean, so basically, if it has uniform convergence, then the empirical risk is arbitrarily close to the generalization error. So the one that minimizes the empirical risk is going to have a generalization error which is within an epsilon by 2 of the true generalization error, and therefore within an epsilon of the best possible generalization error. Right? Okay, great. Now, I had originally said that the sample complexity for agnostic packed learning is upper bounded by these functions of d, epsilon, and delta. Right? But this is not what we have proved. Effectively, if you try to work it out, then what we've really shown is that the sample complexity is upper bounded by some constant times something that grows like d log d plus some function of delta and epsilon. Right. Now, proving this requires some more techniques. Again, better concentration inequalities in some sense, but it uses like vastly different techniques. Something, just an improvement of McDermott's inequality is not enough. But the lower bound, again, we won't cover either this exact upper bound or this lower bound in the course. But certainly the textbooks that I mentioned, they contain at least some hints as to how to prove these. Right. Any questions? Okay. So far what we've seen is that suppose someone gives you a hypothesis class, then you can say whether that hypothesis class is pack learnable or not, because you can find the VC dimension. If the VC dimension is finite, then it tells you that it is pack learnable, but it also gives you a bound on how many samples you need in order to be able to effectively learn it. Right? And that's one thing, but also you know how to effectively pack learn it. You just use empirical risk minimization. Correct? But all of this is assuming that you have a given hypothesis class. Right? The hypothesis class only gives you, it gives you a bound on the generalization error, but all it says is that you can, if you do ERM with a sufficiently large number of samples, then you can obtain the best possible, something close to the best possible generalization error within your class. So if VC dimension is D, which is finite, then and you use ERM, then the probability that this is greater than or min R of H over all the hypotheses in your class plus some epsilon is less than or equal to delta H of epsilon comma delta. Okay. So given a hypothesis class, you know what to do. But now, how do you best choose your hypothesis class? Right? How do you distinguish between two different hypothesis classes? One thing you can do is, okay, I have two different hypothesis classes. Let me choose the one with the smaller VC dimension, because that effectively tells me that it has a smaller complexity. But then that's not good enough, because it tells you if the VC dimension is small, then it has a lower complexity, and therefore the ERM is going to perform within the best in the class. But how do you know what is the best in the class? It could be that the first class has a better minimum generalization error than the other, but a priori you don't know. Right? So this is something that you can never compute, because you don't know what the true distribution is. So then how do you select your model, or how do you select your hypothesis class? Right? So there are a number of different ways to do this. Again, we don't have enough time to cover everything in this particular course, but I'll just tell you what people do, what you can do in such scenarios. The first the question is, how do we select a model? Select H, right? So in particular, let's say that, for instance, so H could be the set of all neural networks with a certain number of neurons. right? So example, it could be H is set of all, let's say, neural networks with one hidden layer, and the hidden layer has k neurons. As you increase k, the complexity increases, and obviously if the VC dimension is finite, then the VC dimension also increases. But at the same time, you could achieve potentially you could achieve a smaller minimum generalization error. So you're increasing complexity, but potentially this could decrease as k increases, right? And in fact, that does happen because it's a known result that if you let k to tend to infinity, then it's a good function. No matter what function you have, as long as it's a smooth function, this class of functions can be well approximated. All right. So now there's this trade-off between the. You have a question? Exactly, it's just universal approximation. Nothing. Right? But of course, universal approximation only if you let the number of neurons tend to infinity. Right? But now what we want to do is we want to know what is the trade-off between complexity and generalization error, right? And minimum generalization error. We know that if we let k to tend to infinity, then that's good because because letting a large k ensures that this is small. But on the other hand, if k is really large, then the VC dimension is also large. So you need more samples even to ensure that the empirical risk is close to the generalization error, or ERM achieves the minimum risk. Right? So essentially, as you increase k, the convergence to the optimum also increases, also becomes slower, because you need something, an n which is really, really large, if k is large. Right? If k is large, then the sample complexity for a given epsilon and delta is also large. Because if k is large, then the VC dimension is large. Right? So one solution, which is generally not used in practice, is instead of doing empirical risk minimization, you look at the collection of all of these hypothesis classes, and in some sense try to find the k and the h within the k that is the optimum in some sense. Right? So right now we're assuming that n is fixed. Okay, suppose that the number of samples that you're given is fixed, but still what you want to do is you don't want to restrict yourself to a particular k, but you want to look in some sense for the optimum h among all possible hk's. Yeah. N is the size of the training set, which R of h exists. You can't, the R of h is something you can never compute, right? The learner can never compute R of h. Which one? Correct, but that is kind of logical, right? because you're assuming that you have a hk which is of increasing complexity, but in this, at least in this particular example, as k becomes large, it can approximate any function arbitrarily close. All right. So in this case, in fact, one can prove a bound on the generalization error over all possible hk's for a given n. So suppose n is fixed. Then what you can show is that the probability that r of h is greater than or equal to r s of h plus the Rademacher complexity of the hypothesis class that contains h plus square root log k of h by n by 2n. This is less than or equal to, so this probability that this happens for even one h in h1 union h2 and so on. A question?
What is it?
In the subscript of this capital H, this is, so this little h belongs to some hk, right? And the k which contains this, corresponding to which h, little h belongs to this capital hk is that, is this, right? One. So in other words, you're looking at an increasing, you're looking at a sequence of hypothesis classes of increasing complexity. So for example, if you look at a class of neural networks with, say, 3 neurons in the hidden layer versus 4 neurons in the hidden layer, H3 is a subset of H4, because you can obtain H3 by just setting some of the weights to be equal to 0. All the weights to one of those neurons can be set to 0. The bias corresponding to that particular neuron can be set to 0, and everything else can be arbitrarily chosen. Right? So this is a bound that you can prove for this sort of growing class of neural networks or growing class of hypothesis classes. And in fact, k doesn't even have to be finite. It could be an infinite sequence of infinite increasing sequence of hypothesis classes. So since this is true, what you can do is, this is your epsilon, right? This whole quantity is your epsilon, and you want to make sure that this is as small as possible. So one strategy is, instead of minimizing the empirical risk, you try to minimize this whole quantity over here, right? So here's a different algorithm than empirical risk minimization. So minimize okay, so I'm looking at, this is a sequence of HKs, right? you have H1, H2, H3, and so on. It goes on potentially increasing sequence. Now for every H, let's suppose that little h lies in capital H subscript k. Then this is exactly capital H subscript k. Right? I could just call this hk, but I just wanted to be a little more explicit. Again, it's square root of log k. All right, if you find this easier, then sure. So little h would belong to some hk, right? It will belong to hk plus 1, hk plus 2, and so on. So for every hk that h belongs to, this bond is true, right? So you can take k to be the k to be the smallest parameter for which little h belongs to hk. For every sequence of hypothesis classes, right? So what you could do is you choose h star to be argmin overall k, h belongs to hk. So you're minimizing both over the complexity as well as the hypothesis within the hypothesis class with that particular complexity of the empirical risk plus the Rademacher complexity, because note that this depends on hk, plus square root log k divided by m. Which one? That's anyway a constant, right? So there's nothing to minimize over. The only free parameters that you have are little h and k. Your hypothesis class is the union of these hypothesis classes. Right? So in particular, what this says is that it's okay if something has a larger empirical risk but a smaller complexity, then you give more weightage to that, you give sort of more preference to that. But at the same time, if something achieves a really small empirical risk but really large, so what can happen? So if k, as you increase k, right, you make k to be really large, then your empirical risk could be very small, but then the complexity is really large, right? So this is not going to prefer that over something that achieves reasonably small empirical risk but larger, like non-trivial empirical risk but very small complexity. So this effectively trades off. It's essentially a regularization term between it is a regularization term. I mean, regularization term in the sense that it depends on k, right? But it is one particular choice of the regularization term, and it's coming essentially from this particular block. Because you want to choose a small epsilon, the way you make this epsilon really small is by making sure that this quantity is really small. Nothing more. That's the intuition behind choosing this. And this particular approach is called structural risk minimization. And this effectively trades off complexity and error. Right? Higher complexity could potentially lead to a small empirical risk, but it could have a large generalization error. Right? And that's exactly what this statement is saying. If k is large, then empirical risk could be small, but this quantity is going to be large, and therefore the generalization error could be much larger. So that's what you can do. The only problem with structural risk minimization is, okay, you can compute the empirical risk, but these quantities are this computation of the Rademacher complexity is going to be really hard. Yeah, question. It is structural risk minimization. Any questions? Which you can't. That's the problem with structural risk minimization. Right. So in the next class, we'll see a different approach, which again allows you to look at different hypothesis classes and still choose the best one among those different hypothesis classes. The next class will be the last class. After that, we're going to have the final exam.